Okay, and our next speaker is Federico Rescigno, who's going to talk about the mean longitudinal magnetic field to understand stellar activity.
Thank you. Okay. And this is working. Perfect. Hi, everyone. My name is Fede. I'm currently a research fellow at the University of Birmingham, which is why Billy is on the stage. But today I'm actually going to take you a bit back in time to my last project during my PhD in Exeter. So we've been hearing a lot, and sometimes you see people brighten up when anyone mentions magnetic fields. I'm one of those people, so let's talk magnetic fields. So we are at a conference called No Thigh Star, No Thigh Planet. So we all agree that to really characterize and detect planets, we need to understand basic stellar characteristics. One of the ways we do this is using activity proxy, activity indicators. They can tell us something about, for example, the rotation period of the star, which is really important, especially in radial velocity, for example. They can tell us about the presence of active regions, spots, faculae, and the sort. They can even tell us information about the stellar magnetic cycles. And all of this information are really, really vital to be able to start detecting and characterizing planets. However, not all activity proxies are born equal. And in particular, we've proven again and again that the standardly used proxies such as the S-index or the full width enough maximum of the CCF are not really effective for quiet stars or for stars that are going through their activity minima. And when I say quiet, it doesn't mean that there's no activity. So we still need to understand what's going on, and we still need to understand the basic stellar characteristics. This is particularly important now because new RV surveys are actively targeting and choosing to target quieter stars for the detection of rocky planets. So it is vital to understand what's going on. So we need new proxies, essentially. We need activity indicators or some kind of measurable value that can inform us about basic stellar characteristics even at the quietest moments of stars. And since we think that the great majority of activity and related stems from magnetic fields, why not start there? Let's go to magnetic fields. How do we measure them in stars? Now, to do that, we need polarimetry. And when we say polarimetry, we mean that we measure the Stokes profiles. The first two, I and V on that side of the plot, represent the intensity and the circular polarization of the light. Then we have the Stokes U and Q. These two represent the linear polarization. All of them together can give us information about the absolute magnetic fields on the stars. Can we use the absolute magnetic field as a proxy of stellar activity, especially in RVs? Absolutely, yes. And actually, there's this paper published by Rafi that proves that the absolute or unsigned magnetic field is a really great proxy for stellar activity in solar-like stars. However, Q and U Stokes are really, really, really hard to measure. And for quiet stars, they might be impossible to do that. So let's put those away, let's shelve that, and let's see what we can do with instead only I and V Stokes, which are much easier to detect in less magnetically active stars. And that's where my work comes in. This is my published paper from last year, and today I'll be taking you through the results of this analysis and my focus on the mean longitudinal magnetic field as activity proxy in the context of radial velocity surveys. So let's get started. We don't have really the type of polarimetric data and time series that we need to make this analysis for other stars. So let us start from the star we observe the most, our own sun. And in particular, I started using SDO HMI filtergrams that look a little bit like this. I use the continuum, the magnetogram, and the Dopplergram. And I essentially take all this data, and using a pipeline that we developed a couple of years ago called Solaster, I go from resolved solar images to time series. And this is the data that I work with. On the top, I have the plot of BL, the longitudinal line of sight magnetic field. I'm going to call it BL because it's very long to say. And on the bottom, I have the RVs derived from SDO. If you're interested about that, I can talk about this for hours. They're special. Please come and talk to me. But for now, let's focus on what we can do with these two time series. And we kind of already see that they kind of map each other. You can see it goes up here, it goes down here, it goes down here. So the very first check that we can do is, do they directly map each other? Are they directly correlated? The answer is absolutely not. All right. So BL and the RVs absolutely do not correlate with each other. And that doesn't change much throughout activity level either. So did we fail? Should we just stop here? Not really, because direct correlation is just a very, very basic check. And actually, I kept looking at that plot from before a lot, and I figured out, well, what about comparing the RMS of BL and the RVs? And this is it. So I started picking wider and wider windows over which to calculate the RMS of BL and compared it to first the RMS of the RVs in blue and then the RVs themselves in purple. And as you can see, once I get a window size of about 27 days, which, oh wow, it's the rotation period of the sun, I get a really, really good correlation. That means that we can use the RMS of BL as a tracker of the magnetic field, of the long-term effects. And actually, I did this test, and with a very, very simple linear decorrelation, I was able to essentially get rid of all the signal of the magnetic field in the RVs. So great. This is one way we can use BL. But really, to check how effective a proxy is, we need to compare it to something that we know works. And that's where the Harps North data comes in. I decided to take the Harps North solar data because we have a good amount of years of analysis here. And in particular, as our standard comparison proxy for this talk, I picked the S index on the bottom. Now, the first thing I want to do is just go through the standard type of analysis we do when we do planet detection, when we try to understand the signals we get from stars. And what we do, we start with periodograms. So let us plot the periodograms for the RVs on the top and from the S index on the bottom. There we go. And as you can see, this is the entirety of the data that we had before. And it's not really pointing us to the rotational period much. But then I do the exact same thing on the same cadence and same data points for BL, and this is what I get. Oh, that's pretty. As you can see, the rotational period, it's popping up fantastically. And we see its harmonics here and here. But this is an FIP of 0.1%. This is lovely. So this looks amazing. Let us go a bit further. Let us do autocorrelation analysis. This is what our time series for RVs on the top and other activity indicators look on the bottom. What we're looking for in an autocorrelation analysis is a series of bumps that are separated by an equal time lag. That can help us understand the rotational period of the star. Now, this is what they look for RVs and activity indicators. I guess you could kind of see something in the SDO RVs, but you really kind of need to stretch to get a good precision. Let us plot BL. That's what we get. We get the beautiful peaked time series, well, lag series, and that can give us a lot, not only about the separation between the peaks, but also about the envelope that we get at the top. All of these results are because the signal in BL is much simpler than the signal in RVs or activity indicators. This is what these plots are telling me. Essentially, these are structure functions. For more information, we can talk to Ben Lakeland, that's also here. But essentially, if there's a lot of types of signals with different baselines affecting the time series, you'll see the structure function going up. However, you can see in the BL, just before this is the solar rotation period, BL stops going up, although in both S index and RVs is still going. This is essentially telling us that the signal in BL is much simpler than the signal in RVs and other activity indicator. And that is because it is not mapping directly, it does not directly correlate to either of these. So all of this is great. We have proven that BL can be incredibly powerful if we have a 5-year time series. We don't really have 5-year time series for the great majority of stars. So let's instead look and take some chunks of data, or about 100 days, 200 days each, at different activity levels. These are the 3 ones that I'm looking for high, medium, and low activity, because I want to check, is BL good at the lowest activity? Can it outperform the S-index and other activity indicators? So let us do a basic program analysis. This is what it looks like at high activity, with BL on the top, RV in the middle, and S-index at the bottom. And as you can see, the S-index is behaving pretty nicely, but we can also pick the rotation period and its first harmonic. It's always going to be like this for BL. Now let us go at medium activity, and already here, BL is vastly outperforming. You got a single peak, that's nice. You don't really know what this peak is, so you cannot really be sure to decide which one of the rotation period is in the S-index. And then let's go to low activity. Here, we don't get anything. We don't really get any information. So is BL bad at it? Not really. I decided to go a bit further and look in the context of GPs. I use my code, I use this kernel, it doesn't matter really. I'm only going to focus on the results we get for the period. I essentially did a GP regression on the time series that I highlighted before, and these are results I get. This is for high activity. These are posteriors. In purple is BL. Then we got the S-index in green and the RVs in yellow. This is medium activity, and this is low activity. That means that every single time, BL has an easy to understand distribution around the true rotational period of the star. So BL outperforms all other indicators that I've tested and the RVs themselves at highlighting the rotation period of the sun. So I'm going to leave you with my summary slides. Essentially, let us do polarimetry. We should do polarimetry of stars to understand their basic characteristics and use them in RV surveys. And if you are not tired about me and Birmingham, please come check out all our posters.
Okay, great. Questions for Federica?
Great talk. Jim Davenport from the University of Washington. So you showed from the high, medium, and low activity states the really nice recovery with BL, but you could see a small shift in the period, or the sort of the mean of the posterior. Is that the latitudinal migration of the spots? Are you seeing the differential rotation on the surface? And do you think this is viable for actually empirically measuring it from other stars?
So we cannot prove that that's what we see because the posterior is a bit too fat. However, we think that is the cause of it. To do this analysis, really, you need to take maybe not as low activity, and you might need, so when it came to this analysis, I got SDO data, which has really, really tiny errors, and to make it representative of what we would get in polarimetry, I injected white noise to a 0.2 Gauss level. So this trying to mimic what we would do, the best thing we could get for stars. So we think it could be, but it's very tricky to prove at this stage.
Yeah, I had basically the same question. If you didn't know the rotation period a priori, how would you fit that posterior if it had multiple peaks like that?
So the behavior for the multiple peaks, you could actually, I checked, and it was the harmonics. So that was a very, very standard, like fully uninformed Gaussian process regression. I didn't have priors on period at all. Not even from other analysis. So in an actual proper proxy analysis, I would after getting results like that, I would double check whether the other peaks are due to the harmonics. And then at that point, if I get a value at value x, and then I get another peak at x over 2, and then another one x over 3, I can then decide to put a prior on the value of x that actually helps me to kind of tighten up and get a better looking Gaussian distribution for the posterior.
Nothing online, I assume. Okay, then let's thank Federica again. Very interesting stuff.